Francina is a professor in the Department of Climate Meteorology and Atmospheric Sciences, and a 2021 to 2022 university scholar. She is a hydrometeorologist, and her work focuses on the interactions between the land and the atmosphere, and more specifically on changes in hydrology and climate due to human modification of the land surface and greenhouse gas emissions. Dr. Dominguez was born in Bogota, Colombia. She has a background in civil engineering from the University of Illinois, specialized in hydrology. She progressively immersed herself in atmospheric sciences throughout her graduate training, postdoc experience, and then as a faculty member of the Atmospheric Sciences Department at the University of Arizona and the University of Illinois. This footing in both hydrology and atmospheric sciences has helped her establish a niche in hydrometeorology, and her work has been funded through competitive grants from the NSF, DOE, NASA, and DoD, among others. She was awarded the NSF Career Award in 2015, the 2018 Henry G. Houghton Award, and 2022 Robert E. Horton Lecturer from the American Meteorological Society, and the Ascent Award from the American Geophysical Union in 2019. So with that, I'd like to welcome Francina. Thank you. Please feel free to share your screen.
Okay. Thank you for the introduction. Okay. Can everybody see my, oh, wait, which one are you seeing? The full
You see
screen?
the proper screen, yep.
The proper one. Okay. Okay, thank you so much for the introduction. So I'm going to talk about convective storms over South America from a land surface perspective. And I want to acknowledge my two former students, Sujan Paul and Devian Shug, because I'm going to show a lot of their results. Okay, so one second. So I'm going to talk about convective storms, and I'm going to begin by presenting why it is important to represent convective storms for land surface processes, and what do we need to represent these convective storms. And then I'm going to kind of flip things around and talk about why it's important to represent the land surface correctly to get these convective storms represented in models. So let's start with the first one, and all of this work I'm going to put into the context of South America, but of course the physical processes are valid for many regions around the globe. So why South America? So South America has some of the most important agricultural regions on Earth. So here in the map you see in yellow are the crops that existed prior to 2003, and then in green are how these croplands have extended from the period 2003 to 2019. There is a vast expansion, particularly in central South America. This would be primarily the La Plata River Basin and parts of the Amazon River Basin here up in the north. So really, really important agricultural production, a lot of soy, a whole lot of soy, and some corn. On the other hand, hydropower is critically important in many South American countries. So the map that you see, I'm showing hydropower plants by capacity. So again, kind of highlighting the importance of the La Plata Basin, which is over here. On the left, what you're seeing is share of hydropower on total electric generation by different world regions. And I'm highlighting in red Latin America, just to show how important hydropower is for many Latin American countries. Some of the largest countries powered by hydroelectricity in the world are in Latin America, both in absolute and per capita levels. So precip is important, right? It's important for agriculture, it's important for hydropower, and I forgot to say, this is mostly rain-fed agriculture in South America. So it's different in some ways from what we see here. Okay, so that's kind of setting the stage. And another thing that you guys have to keep in mind is that the basin that I'm highlighting, the La Plata River Basin, has some of the strongest storms on Earth. So this is a map looking where you see the reddish colors are where you have some of the strongest storms on Earth. You see them here in Africa, and you see them also in South America, southeastern South America. And the reason is that there's all these ingredients that converge in this region. So on the one hand, you have mid-level air that crosses the Andes, so it becomes dry, and then as it comes down to the basin, it creates a capping inversion. So this is a way that the atmosphere can accumulate energy before convection actually initiates. On the other hand, you have waves that traverse the region that kind of help convection, and you have a lot of moisture coming from the north via the South American low-level jet. So these things come together to have these good ingredients for convection to occur. And as a result, a very significant part of precipitation comes from the system that we call mesoscale convective systems. So here in this map by Rasmussen et al., I'm showing the amount of rain contribution by different types of storms. And so this WCC are wide convective cores, which is just a type of mesoscale convective, to identify mesoscale convective systems. So just a very large percentage, up to 80% or 90% in some regions of the precipitation comes from these systems. And so if you were to slice one of these systems up, they're gigantic. And what they are complex thunderstorms, which they become organized. So they're much larger than individual thunderstorms. So that, like, they initiate, they organize, converge, and then they start moving. And these are really important actually here in the Midwestern United States, and they're very important in the La Plata River Basin. Now, okay, just to kind of start the discussion, climate models, those that participate in the IPCC reports, or the AR5 or AR6, they cannot capture these systems. So they cannot capture convective initiation, organization, and movement. So this is a really active area of research to try to really better represent and understand and represent these types of systems. They're so important for precip in regions where precipitation is extremely important. So this was the motivation for the Relampago Field Campaign, which was a very large campaign that occurred end of 2018, beginning of 2019. More than 100 scientists converged into Argentina, the Cordoba region of Argentina. And so we had radars, the Doppler on wheels. These are, we had, I think it was 4 of them or 5 of them, and people on the ground. And in the hydrometeorology team, which was where I was looking, so where most of the scientists were looking up at the storms, our team was looking kind of at the impacts of these storms on hydrology. So here you see one of our collaborators, Marcelo Garcia Jr. So he is looking at a stream and measuring stream flow there after a rainfall event. And a critical problem here is that these basins were not, they didn't have observations of stream flow, so they didn't have rating curves. And one of the first things that we had to do was create the rating curves for these mountainous basins. So this is what we're doing here. And because of the types of storms that happen here, the rivers are prone to flash flooding. And they have huge impacts on the people, the communities that live in those mountains. So trying to better get a handle on both the convective storms and what are the impacts of these storms on the ground, on surface hydrology. So in addition to the observation where we got these observations of stream flow for different basins in the headwaters, we also did a modeling exercise where we use, so the region that we're talking about is, do you guys see my mouse here? So this is the region that we're looking at. These are called the Sierras de Córdoba, and we did a modeling study with Wharf Hydro. It's a model that we can couple to WRF, which is the atmospheric model. And we looked at how WRF Hydro was able to simulate stream flow in these basins. So here I'm just showing you one of the basins here. It's Quijinzo River, and the black are the observations that we were able to gather for one of these storms that occurred November 26th of 2018. And these different lines are how different input of precipitation into Wharf Hydro resulted in different stream flow estimates. The key idea here is that in order to get even close to the stream flow, we needed to get to very high resolutions in terms of the atmospheric model to reproduce that precipitation. And then if we really wanted to get the peak and the timing correct, we needed to do data assimilation on the atmospheric model. So once we did that, so this orange, so the black is the observations, and this is the, so this is the ensemble of different atmospheric, the WRF model inputs using data assimilation. That's what really got us the best forecast for the stream flow in this setting. Okay, so that was the exercise for the Relampago campaign. So the key message that I want to get out here is that you need to go to very fine scales that we call convective resolving scales to represent these extreme convective events. So, and the key wording here is convection resolving, where we don't use parameterizations of convection. We actually let the equations do their thing. So here I'm showing you even 12 kilometers. When you go to 12 kilometers, if you are parameterizing convection, if you're using an approximation for convection, you get precip that's too localized, too weak. The systems don't move, so you don't get the storms correctly. Once you get to resolutions of about 4 kilometers, where you do not use approximations, things start to look much better in terms of the intensity, in terms of the propagation. So it seems to be this magical switch where we can better represent convection and precipitation. And just to give you an idea, so here I'm saying 12 kilometers is not enough. CLiMAS models are on the order of 1 degree, so about 100 kilometers. So much, much coarser than what we would need to properly resolve convection. So this idea about the need for convection permitting modeling, particularly in these regions like in these parts of southeastern South America, where convective systems are so important, where mesoscale convective systems was so important. This was one of the motivations for an effort called the South America Affinity Group, which began in 2019. This is led by NCAR. So bringing people together. So these simulations, they're expensive, they're difficult to do. So and so NCAR has the capacity to do this, but they don't have the capacity to analyze all of the data that they're producing. So a lot of researchers from South America, North America, Europe have come together to kind of guide the effort and to use the data that's being produced by NCAR. So rather than talk about this, I'm going to show you a video where we explain what we're doing here. So let me try to do this.
South America's hydroclimate sustains vibrant communities and natural ecosystems of extraordinary biodiversity, including the Andes Cordillera, fertile plains of the Lata Basin, the Pantanal, which is the world's largest tropical wetland, and of course, the Amazon forest. Global warming and land use change are endangering ecosystem health, exacerbating hydrometeorological extremes, and threatening water and food security for millions of people on the continent. The South America Affinity Group, or SAG, was established as a community effort focused on improving hydroclimate science over the continent. At the core of the SAG effort are 2 climate simulations that represent historical and future climate with unprecedented detail. Our goal is to support better informed decision-making. We will present model results for winds, moisture fluxes, clouds, and precipitation over the continent. In northern South America, tropical low-level winds from the east traverse the Amazon and veer south, forming the South American low-level jet. In the south, intense winds from the west form large systems. These winds carry moisture. Most of the moisture is from the tropical latitudes and is transported south with the low-level jet. You are about to see model simulations of clouds and precipitation at unprecedented resolution. Taking a closer look at the Amazon, we see a clear diurnal cycle of convection. We also see how clouds organize over the Andes and some larger convective systems that form. If we remove the clouds, we can see the precipitation. Rain is very frequent over the mountains and over the Amazon basin. Moving to the southern mid-latitudes, we see an atmospheric river from the Pacific that encounters the Andes Mountains. We also see convection initiating on the eastern side of the Andes to form a large traveling mesoscale convective system, or MCS. The atmospheric river brings rain to the Andes, while the MCS reigns over the La Plata Basin.
You enjoyed that. Okay, so we have these amazing runs, right, that are able to capture all this detail. Now we want to see if they're correctly representing some of these details of the land surface processes that are important for convective storms. So previous research that had been done in the Sahel, so remember I told you that the Sahel also has all these intense systems. So previous research had shown that storm initiation is enhanced over dry soil moisture patches. And this is a diagram from Taylor et al. In 2011, where they show how you have a patch of dry soil moisture that allows this buoyancy and instability to trigger convection, and you have moisture that is then converging at low levels and is able to contribute to that convection. And our question was, can soil moisture heterogeneity provide an organizing mechanisms for storm development also in South America? And so first we did this with observations. We wanted to know if this was the case, and this is work done by Divyansh Chugh for his PhD. So we identified convective initiation using geostationary infrared brightness temperature. And then we wanted to understand what were the soil moisture conditions prior to this initiation. And to do that, we used SMAP, MODIS, and AMSR2. And one of the things that I do want you to realize is that we're kind of rotating all of this so that the low-level winds, the dominant low-level winds, are coming from down in the page to up in the page. So first, these are just all the convective initiation that we identified for the period 2001 to 2020 on the order of 80,000 individual events, primarily up in the north, in the northern part of the La Plata Basin. And they have this very clear diurnal cycle where they peak between noon and 4 p.m. local time. And when we look at the underlying soil moisture ahead of the initiation, so the morning soil moisture ahead of initiation, from SMAP, we see that convection initiates preferentially on the dry side of strong, dry, wet soil moisture boundaries. So here you just have kind of this bullseye of where convection initiates. And then we used both MODIS land surface temperature anomalies and AMSR2 to verify that this could also be seen in terms of the surface temperature. So you have kind of these dry, hot condition, a patch of dry, hot soil moisture, soil conditions, which is where initiation tends to happen. If you have a larger patch, so if you have strong winds, so stronger background winds, you need a larger patch of soil moisture to give initiation that kick. So while these could be for light winds, the patch would be on the order of 30 kilometers. For stronger winds, it would be on the order of 100 kilometers. So think about it. A GCM grid cell is on the order of 100 kilometers. And we're saying that convection is initiating associated to patches on the order of 30 kilometers. So you definitely need to go to higher resolutions to capture this behavior. And this is also seen in the precipitation. So, and this is where things get a little bit complicated. So when you have weak background wind, and you have this dry patch, you have convection, and then precipitation kind of is anchored to that dry patch. But when you have kind of stronger upper level support, what happens is that these systems are able to propagate in space. So it rains far away from that initial dry soil moisture patch. So depending on the atmosphere and how that supports the storms, the feedback between soil moisture and subsequent precipitation can be local or remote. Okay, so kind of in summary for this part, our results prove that mesoscale circulations can be induced by soil moisture heterogeneity, and that this is important not only in the Sahel, but also in South America, and that the eventual location of precipitation that occurs associated to these storms depends on the propagation and the strength of the background wind. And finally, how do these kind of SAG simulations, the 4-kilometer SAG simulations, are they able to capture this process that we say is important for convective initiation? And so basically what Devyansh is currently doing is he's repeating the analysis that he did with observations using the model. So he finds that the convective initiation does have that spatial pattern with higher convective initiation in the northern part of the domain, and it also peaks in the afternoon. However, there's a bit of a discrepancy with the model having a higher proportion of nocturnal initiation than the observation. So we're trying to look into that and seeing if it's not a matter of the threshold that he's using. And when he looks at the soil moisture, WRF does show a clear preference for convective initiation near the downwind edge of the dry soil moisture patches. So it's kind of realistically replicating this behavior that he had found with observation. So that's good. And in addition to that, with the model, we have a lot of other things that we cannot have with observations, which is we have the sensible heat fluxes. We can really see if these mesoscale cells are forming. So we have all this richness of information that's going to allow us to really dissect what's happening. So this is work that's ongoing that Devyansh is pursuing right now during his postdoc. Okay, so in conclusion, we need to go to high resolutions to really capture these events that are so critical for precipitation over the La Plata Basin. And furthermore, these high resolution simulations are also allowing us to capture the process by which convection tends to initiate over the dry soil moisture patches, where you can have instability, ascent, and convergence from the wet patches that are surrounding it. And that's it. Thank you so much.
Great. Thank you so much, Francina. So we have we have time for questions. Feel free to drop your questions in the chat or just unmute yourself.
I have a quick question. So you mentioned the fact that when the storms start in that dry area, and if you have a strong wind, they actually move quite a bit before precipitating.
Yeah.
And so do you find that there is places that are individually more likely to just propagate storm after storm after storm in certain seasons or times? Like, are there topographic locations that make that place ideal for continuous propagation?
Yeah, that's a really good question. So, okay, so here, so this is the best way to understand. There's this topographic feature called the Sierras de Córdoba. That's where, you saw when we were looking at those streams that we were looking at mountain streams? That's this topographic feature. And what happens is that you get organization close to these mountains, and then it initiates and then it propagates, and they tend to move in a direction north and east. So as they move away from the mountains, they rain more and more. So this region over here is actually surprisingly dry, but as you move north and east, you get wetter and wetter. There's a strong gradient of precipitation, and that correlates well with this movement of these storms. So that happens here in South America. And actually, that's why the Relámpago campaign kind of converged there, because we knew that convection tended to initiate there. There was a previous campaign that occurred in the United States, and you don't have such an organization feature in the US, a topographic organization feature that's that clear over the Great Plains. So in the Great Plains, convection tends to initiate in kind of random places, and it makes a field campaign really difficult. So the Pecan Field campaign was only able to capture a couple of events, whereas we captured like 10 or 12. So the organization of the topography is critical for these types, for South America.
Cool.
Did that answer your question?
Yeah, no, that answered it. Thank you.
Thank you.
Any other questions?
So this is Praveen. So Francina, those simulations that you showed, those amazing simulations, those the visualizations, they were done by David Bach at NCSA. Is that correct?
Yes.
Yep.
Yes.
Yep.
Absolutely. Yeah, that's the visualization magician is David Bach. Yeah, so we started working with him on some coarser resolution simulations years ago, but now with the higher resolution, yeah, he's able to bring out just so many other features. Yeah, and we're actually trying to go now even finer to individual events. Yeah.
Thanks.
Aaron Bauer. I think there's a question by.
Yeah.
Aaron?
Aaron, did you have a question? Yes. Maybe she disappeared. I think someone else had a question. Marian?
Yeah. Very nice
Okay.
presentation, and I'm excited to see David Bach's visualization. We start an exercise for our project, and that scenario of coming in layers from up down, for us, it's a watershed, a small watershed level. It's excellent idea for driving our animation. My question, though, so yeah, and overall, nice presentation, but I'm not a hydromet guy. I am not a numerical guy. I'm working in river, so I have maybe a naive question, but one is, which I see it in the river actually, very important for capturing processes occurring over scales, time and space, is very important to look in the proper windows of time and scales. And I found very illustrative the convective resolving scale term which you use now to see your processes of interest. My question is, you will use modeling works, of course, works well if it's validated. For validation, you need data. Now, how do you go in this type of experiments? How do you design the experimental design? The storms are, of various intensities, various timescales. How do you design the experiments to capture those convective resolving scales to really support the modeling?
When you say the experiment, is it like the observations that we did in the field?
Yes.
Is this what?
Yes.
Okay. Yeah. Okay. So this is a really good question because it involved working hand in hand with the forecasters. So because our experiment, there were most of the people there were atmospheric scientists. So part of their goal was to, as soon as they saw that the conditions were ready for these storms to occur, they would take the radar. So there's like a forecasting center that we had in a town in the mountains, and then they would get ready when things were starting to converge and bubble up. They would send the trucks. So we would be there kind of waiting to see what happened, if convection actually did develop. And so we had a window of about 5 hours from the time that we knew convection was initiating until we knew that we would get the response in the place in the river where we had set up instrumentation. So we knew more or less the window, and we knew this window because we had talked to the people in the mountains. So we knew, like, because there were no previous observations of stream
Yeah.
flows.
Mhm.
So then it was literally like the firefighters that would tell us, oh, if rain starts, then we have about 5-6 hours. Okay. So we knew that we had that window of time. So as we saw that the precip was developing, we were like, okay, we go now. So then we had everything ready to go and measure when the storm did occur, so that we had the entire kind of, so we were able to get the rating curve so easily, but we knew where the storms were happening because we had a whole team that was focused on the storms, and our team was just waiting for their green light to go.
Mhm.
It was really cool. It was a wonderful
But
experience
yeah,
to do that.
you need knowledge of this, and you said that you talk to people on the ground to find these patterns, right?
Yes. Yeah. And we needed their help in terms of so if there were locations that we were not able to get to with the instruments, we also had particle image velocimetry. So then they would take like video. So we had people that were trained to take the videos in a particular way so that we could do PIV with those storms. Yeah, it was super cool. I learned a lot, and it was really Marcelo Garcia, the Argentinian researcher that you see there.
Yeah.
He was in charge of all of the stream flow observation part. So it was a great experience. Yeah.
Thank you.
I think Aaron.
Hi there. I was curious if you have, you talk about scale, if you have an idea of what your, the different scale sizes, and if they have a minimum scale, maximum scale,
So
to your,
yeah,
to
when
get
you
this resolution.
Yeah, so there's been quite a bit of work on this. So okay, the 4 kilometer scale seems to be kind of a sweet spot. But the main thing is that there we turn off the approximation that is used in most climate models, which is this convective parameterization. So once you turn that off, and that can only happen at scales below about 9 kilometers. So once you hit about 4 kilometers, that seems to be like a really good place, like cost benefit analysis here. Once you go to finer scales to like 1 kilometer, there doesn't seem to be a whole lot of benefit to do this. This is still ongoing. Like we don't have a definite answer, but for some reason, going from 4 to 1 just doesn't give you as much benefit as you would expect from the much larger cost of going
So my
to
other
1.
question, I'm sorry, I can follow up.
Yeah, sorry,
Okay,
yeah.
for everyone. So could it be the scale has to do with maybe the elevation, above the ground that the systems are developing and are reacting? Because I'm just trying to conflate what you're doing with what we would do here in the Midwest, where we don't have these mountain ranges. We have our wet spots are floodplains and rivers.
Yeah.
Yeah, so I'm thinking like could that scale wouldn't necessarily translate to here, but I'm interested in looking into that.
It does actually. So that 4 kilometer scale kind of sweet spot, it was, so NCAR did a bunch of tests for the United States, and that's where they found the best representation of these, of the hydroclimate. But it does work here. The 4 kilometer
Okay.
scale And there is an analogous simulation to the one I just showed. There's one for the United States. It's called the CONUS 404.
Right.
So, yeah. Yeah, so my answer was going to be like you also need to represent topography quite well, but you're right that for the Midwest, it would be my hypothesis would be that the land surface heterogeneities would be even more important because those would be the organization structures, like
Yeah. So I have a very dense network of precipitation gauges with a long-term data set that I'm actually having David Bach and his group do a visualization for.
Okay.
Yeah, having worked on the data for over 10 years, it's very I see these patterns that these storms are picking up the moisture from the river and the floodplain, and then it goes up a small elevation bluff compared to what you have.
Yeah.
And then it drops it immediately close, like at the top of the bluff, and then further away from the river, it's drier. So,
This is in Illinois?
yeah, it's in Illinois. Mhm.
Okay. Okay,
Anyway,
that's
so
cool.
that's very interesting. I'd love to talk to you about this, but I don't have I haven't done all this other analysis, but I just have the rainfall data in a dense grid.
Well, you could also look at the CONUS 404
Oh,
simulations.
yeah, I will. Yeah.
It might give you something.
Mhm.
I don't know if there's any more questions.
Hi, Francine. I have a scale related question kind of to that. So you mentioned the 4 kilometer scale being kind of a sweet spot, and you're able to like turn off these parameterizations and let like, a more realistic process take place. Is that true for like all types of rainfall, or is it very specifically on these types of convective storms?
So when you have like frontal systems or just larger kind of low pressure systems, the scales are much larger. So so the models do much better at those kind of other types of storms when where the forcing is larger than the grid scale that you're using. So they're much better, yeah. I don't know if there's any. I think that's it.
Okay.
I have potentially one more. With climate change wise in this area, are you guys noticing these storms getting larger or like more common, or like what are the changes that we're seeing in this region?
So we have not finished the analysis of our simulations. We do know that kind of similar to what is happening all over the globe, you have a northward shift of the jet stream. So what that means is that precipitation patterns are intensifying, like they're moving a bit towards the poles. And you also have drying in the subtropics. So we're seeing that in South America as well. There is intensification of precipitation over the La Plata Basin. But the observations are they're not as good quality as we have in other parts of the world. There's many fewer stations to really get a clear signal. What we expect to find, so we have the historical simulation, which is what David Bach visualized, and then we have the climate change simulation, which just finished. So we just finished the one with a warmer climate, and we're going to look at what happens to these storms in the warmer climate simulation.
In that simulation, do you shift the location, like you said, it was shifting towards the poles? Do you think that will actually have an effect on that, like localization of where storms often start in this region, since topography is important?
That's a good point. I don't know. I'm not sure what would happen, but yeah, that's a good point.
Interesting. Okay, well, thank you.
Leila.
Hi, Francina. Thank you so much. This was a great presentation. I also love the visualization and the music. It was
I
wonderful.
I want to put a plug here. This is a Colombian musician who's an expert in Andean music. So sorry, yeah.
Wonderful. And my question is more related to the transitions in the land cover. So you mentioned the expansion of the agricultural transitions into more soybean land, and I am wondering how that match your results.
Yeah, so this is also we're very interested in this particular question, Leila. So what happens when you have a transition to soy in this region is that these are rain-fed regions. So uh, in general, the transition is from pasture to soy. So you go from like deeper rooted plants to shallower rooted plants that are annuals as opposed to perennials. So the big change that is happening is that you have less transpiration overall. So over the year, you're going from about 1,000 millimeters for the pastures to about 600 millimeters of transpiration for the soybean. And as a result, so you just have less fluxes of moisture from the land to the atmosphere, and you're having an accumulation of water in the subsurface. And you're seeing greater flooding in the region as a result. And there's a beautiful paper that came out in Science recently that showed really like when you those regions that are transformed to soybean or to crops, they get flooded. They get flooded. You can see it in the satellite imagery. So that's I think it's kind of difficult for us to think about it because the processes are quite different from what happens in the plains of the United States. But over there, land use change has resulted in more water accumulating below ground and more flooding. So when a precip event does occur, you have greater tendency for flooding. So it's fascinating what's happening. Yeah, there's a whole lot of changes, and I'm very interested to understand. So then what does that mean for the atmosphere when you have these changes in the surface and subsurface hydrology?
Thank you, Francina.
Any other questions?
So I'm not so familiar with all these models and the data that you've gotten, and I missed the beginning of your talk if you covered it, so forgive me. But does it include various, how low does this in elevation is the data resolvable? Can you resolve?
Are you saying below ground?
Like you know, off the ground, like how
Hmm.
like what's the limitation? Like where's your limitation for how low? I know you use trucks with radar, so I mean close to the trucks it's like basically near the truck, but like when you're getting farther away, like what's your elevation off the ground for resolving the atmospheric data?
Are you saying from observations or from the model?
From the observations.
Oh, from the observations. Okay, so that when you have observations of the storms, you have an angle. So the further away you get from the trucks, the
Right.
higher that you can look. But I don't know off the top of my head. And I know that there's the topographical issues as well, that when the trucks are looking towards the mountains, there's also all sorts of issues there. But off the top of my head, I wouldn't know.
So how far
Exactly.
apart were the trucks? I'm just saying, like, do you know like what when you resolve for the model, when you resolve the model with the data, what was your elevation then? Like maybe that's a better question.
So for the model, we have, I think it's 60 levels, and I think it's 20 within the boundary. So we have a lot of levels within the boundary layer. So in the first 2 kilometers of the atmosphere, we have quite a bit of resolution there.
So
but of course,
how low does your
observation.
model go? How low does your model go?
Oh, so it has to do the whole thing because it
Right.
has to have the surface, it has to have the subsurface. So it's a continuum.
Okay.
So you go from
Right.
-2 to, yeah,
Okay.
up. Yeah. How well we do it, that's another issue. But in theory, we have to look at all of it. Yeah.
So yeah. I just wondering what you're doing in the gaps in like the farthest point between your trucks for the radar, like how high that was. Because you're estimating everything below that, the intersection of the cones.
Yes, yes. And I think maybe a clarification is that the data of the trucks is not ingested into the model. So
Oh,
they're
okay.
independent.
Okay.
We use them to validate our model, and they have a much higher resolution in terms of
Mhm.
what they're doing than what the model would provide. Yeah,
Okay.
but they're not talking to each other.
Okay.
Yeah. Leila.
Francina, one clarification. You mentioned that the Sierras de Córdoba is actually kind of dry. But are there other key ingredients for that place to be dry when they have high convection? Or, I mean, the strong storms that fall there are not able to keep moisture for it to be wetter?
Yeah, so this was very strange when I arrived there because I knew that some of the strongest storms on earth are here, and when I get there it looks like New Mexico. So I'm like, what is going on here? So then I understood that what happens is that you have initiation, but most of the time the rain is further out into the plains because these storms migrate. So that's a critical thing to understand, that the storms don't stay in one place. These organize, and when they're mature is when they're giving out most of the precip, and then they move. So that's a critical thing to understand. Precip moves with these types of systems.
Right, so they can be the source, but they are not always the final destination of the. Right,
Exactly. Yeah.
thank you.
So the range, you saying it looks very much like New Mexico there, and so is it very sandy right there? Like, is that the thing? Because the area where I have it's very interesting. A lot of the parallels with the region,
Yeah.
and I have this precipitation state, but where my rain is falling, and I'm talking about, it's very sandy.
So this is a soil map. So at the higher elevation, sandy loam, and then here loamy sand. That's what we are ingesting into the model.
Okay.
Yeah.
Thank you.
Okay, I think that's what we have time for. Thanks so much, Francina, for the excellent presentation, and thanks everyone for joining this morning. Have a great weekend.
Bye-bye.
Bye.
Thank you, bye-bye.
Thanks, Francina.
Bye-bye.
Thank you.
Thank you.